All right, so a couple of quick announcements. First of all, about the midterm. You'll notice if you went online and looked at the lectures, I've delayed the date for the midterm to Thursday as opposed to next Tuesday. And reason being, the homework, a couple of people came to me and said they'd like to look at the homework solutions before the midterm. So now you'll have the solutions to this last homework assignment before you actually take the midterm. Okay. Questions or comments? I hope nobody has has favoritism for Tuesday and is upset about this. Chris?
As far as on the midterm, a lot of stuff we did in the beginning, you said sort of we didn't need to understand. Is there like it was the device stuff?
Yeah, that's true. Yeah, so the device stuff is more background material for the course. You don't have to know it in detail, and it's very unlikely that I'll ask you a device question. Uh, Circuit stuff that we've been doing is really the more important stuff.
So like everything after the first lecture.
Pretty much, yeah. I think the first 2 or 3 lectures were device, but certainly the homeworks, with the exception of the first homework, have been, very relevant. Okay. Other questions? And probably on Tuesday I'll do a quick review of what you should know for the midterm, so I'll give you a little bit of heads up. And it's better for me to do that on Tuesday because at that point hopefully the midterm will exist and I can help you a little bit more. Okay, other questions? All right, so if you missed the announcements, if you're just coming in, the midterm is moved back by 1 lecture, so next Thursday. Okay, so let's get back to feedback. So last lecture we took a pretty complete look at the 2-port approach to feedback analysis, and in particular I started doing an example, and I'll kind of go back to that example. The example we were looking at was a 2-stage amplifier where we sample the output voltage and connect our feedback network in series with our input. So we do a voltage subtraction. And so this is a voltage amplifier. And so if we try to use, let's say, the hybrid parameters that we derived last lecture to analyze the circuit, just out of curiosity, did anybody try to do that, and what kind of results did you get? Okay, anyone try it? Okay. Well, in that case, I'll still leave this for you because it's an interesting example. It does, if you're going to be taking a test next week, it's a good hint to go home and do this thing. Make sure you understand the technique. But what's interesting about this example is that, let me just give you a hint. So when you do this example, when you're done, do it the other way. Do it with return ratio analysis. We're going to talk about that in today's class. And you'll get a different answer. And you'll have to go back and forth and understand why you're not getting the right answer. And part of the answer has to do with the fact that, we talked about this last lecture. When we have our H parameters, let's say, this is the 2-port that we have. And if you look at this 2-port, besides the polarity of these 2 inputs, everything else is very symmetric, right? If I apply a signal here and ground this terminal, then the input impedance is the same. I just see this Z11, let's say. On the other hand, and the gain is going to be the negative of the gain if I ground this terminal and drive over here. But the input impedance is the same. Well, with our transistor, it's actually quite different. So let's say even our bipolar transistor, if I ground this terminal and look in here, I see at low frequencies R pi. If I ground here and drive on this terminal, then I see approximately 1 over GM. Depends a little bit on what's on the collector, but to first order, it's 1 over GM. And so the polarities of these 2 inputs are different, but the impedances are very different. So you can see that our transistor does not easily fit into this model. And why is that? Yes, I mean.
It's an active device, so from different points looking into the active device, you see different impedances.
Well, not quite, because I'm talking here about small signal parameters, right? I mean, I could very easily come up with a small signal model that's linear, that has the same behavior. Yes, David.
Is it because you on the diagram you separate the primary from the secondary?
Yeah,
You know, if you show
exactly.
them, it will be the same.
Exactly, yeah. So if I make this connection here, when I excite this terminal, this GM generator can push current into this terminal, and that changes the impedance levels. So the key difference is that these terminals in a real device are different. So if I analyze this circuit and I put my loading on the emitter side, turns out you'll get the right answer. If you put the loading on the base side, you actually will get the wrong answer. So I invite you guys to look at this in more detail. We're going to take a different perspective today, which in some ways is nice because it doesn't depend on these sensitivities. So the return ratio procedure of determining the loop gain and the closed loop gain is somewhat agnostic to how you actually define your two-port. You don't have to call it shunt or series. You can basically just do the analysis and interpret the results. So let's look at that. Okay, so the idea for the return ratio analysis is that we break our loop at some point. And as we discussed last lecture, the best point to do it is some controlled generator. And I'll just draw this as a controlled generator to make that clear. So let's say this controlled generator has a gain K times some controlling voltage SIC. Okay? And this is my output. And somewhere over here I have my input. And notice that instead of writing V's and I's, I'm writing S's. Because really these are, they could be voltages or currents. So this is what's inside this box is the rest of the feedback amplifier. Okay? And very briefly, the way we did the return ratio analysis was we break the loop exactly at this controlled source. So instead of putting in a controlled source, we put in an independent source at this point. We observe the signal that returns over here, multiply it by K, take the negative, and that's our return signal. And the claim was that that's actually the loop gain of the system. Intuitively, that makes sense, right? You inject a signal into your loop, you break the loop, you look to see what signal comes back. By definition, that's the gain that you get as you travel around the loop in the circuit. What we'd like to do today, though, is to extend that and show that, first of all, by doing that calculation, you can find not only the loop gain, but you can also find the input and output impedances and the closed loop gain. Okay? So here's some very simple, obvious equations. I'm going to call this voltage SOC. So this is the output of the control generator, which is just K times SIC. And for instance, K is usually equal to GM for most transistors, right? We're going to break the feedback loop at the GM generator of the transistor. And also what we're going to do is, might seem a little bit funny at first, but then it'll make sense. For the time being, I'm going to treat this port as if it were an independent port. So independent voltage source. And so if I look at this circuit, I could say that therefore any signal in this circuit is just a linear combination of the two independent sources. So for instance, SIC should equal to B1 times Sin minus H times SOC. Right? Sin is an independent signal, SOC is an independent signal for the time being. And so therefore SIC, which is just a signal inside the circuit, is just a linear combination of these two independent sources. And again, bear with me with the notation, right? Why not just call this A1 and A2, right? You could. I just want to be consistent with Gray and Meyer where these equations are developed. Okay, likewise, if I'm interested in the output voltage, well, that's also a linear combination of Sin and SOC. So S, again, I have call this D, Sin, and then B2, SOC. Okay, any questions? So this is very simple. All I'm doing is saying this is a linear circuit. Let me treat these as independent sources, and then I just write these two signals, which are signals I care about, right? Ultimately, I care about the output signal, and I care about this internal signal, because really this is not an independent generator. Ultimately, the voltage generated here is just K times SIC. The nice thing is that when I treat this as an independent generator, I've broken my feedback loop. Okay? And so you can see very naturally that this signal here is going to be related to the return ratio. Okay? So let me just now write a few simple equations from here. So from here you can see that B1 by definition is just SIC over Sn when SOC is equal to 0, or SIC over Sn when K is equal to 0. So setting K equals to 0 is equivalent to basically killing the loop gain in this circuit. And so this is, if you like, this is the partial gain from the input to this important controlling terminal when when the generator has been turned off, right? And likewise, I can define H, or I can write an equation for H, which is SIC over SOC minus when Sn is equal to 0. So if I look back here to my circuit, you can see that this is, if I short the input, apply a signal here, and then observe what comes over here, this is kind of like a reverse gain, right? This is something maybe a little bit undesirable. If I put a signal here, some of it is feeding back through here and appearing here. Okay, so let's call this a reverse gain. All right. Finally, from the second equation, D is S out over S in when SOC is equal to 0, or equivalently S out over S in when K is equal to 0. So what's D? Any physical interpretation for D? Gain under what conditions? Okay, you want to use a mic?
Under the closed loop condition?
No, actually it's the opposite, right? Because I've set K is equal to 0. So that means the GM is equal to 0. Right? So this is almost like the direct feed-through. So the D should remind you of direct feed-through. It's the feed-through. If I set this generator equal to 0, right? So this is not there. Apply a signal at the input, see what comes out at the output, right? And so usually this is actually feed through for most amplifiers through a passive network. So this would be like C mu, feed through from the input to the output without the active device, active, so to speak. Okay? And then finally, this last term, B2, is simply S out over SOC with Sn equal to 0. So this is also a partial gain from here to here when the input is shorted. Okay? So from generator to output for input shorted. And this term here, B1 and B2 are kind of like cousins. B2 is the gain from, so let's say gain from input to control node for K is equal to 0, for generator off. Okay? Okay, so this is actually quite trivial. We just have defined a bunch of things without doing anything interesting. So let's start doing something interesting with these concepts. All right, so let's actually number these equations. to make it a little bit easier to follow. Let's call this equation A, this equation B, this equation C, D, E, F, and G. Probably won't need all of them, but just for completeness. So let's take equations A and B together. Let me come back here and show you equations A and B. So equations A and B, if I just plug in for SOC here, so here SIC plus H SOC is equal to B1 SN. Well, SOC is just K times SIC. So I have SIC 1 plus KH is equal to B1 SN. Or I have an equation that says SIC over SN is B1 1 plus KH. Okay, so some simple algebra. And then now let's take equation C. Equation C is S out is a function of Sn and SOC. Let's again substitute, so I can have S out over, let me just rewrite it. So S out is equal to DSN plus B2 SOC. And so I can write S out over Sn is D plus B2 SOC over Sn. That's SOC is just K times SIC over Sn. And this I just derived here. So I have the total gain is B1 K B2 divided by 1 plus KH. So let's call this A, the closed loop gain. Okay. So all we've done is very simply, based on this formulation, based on defining all these variables, calculated what the closed loop gain is, right? So far we really haven't accomplished that much. All we've done is define a bunch of new constants that we have to get familiar with. But as we'll show you, this form of the equation is actually very insightful. It tells us, basically it puts the system into a form, into a block diagram form. Already you can recognize it, right? You can see the denominator that has feedback, but also it has feed forward, direct feed through. And this is this term here, D. All right, so let's show you that that's actually the case. Okay, so first of all, what is KH? That's the denominator here. Okay, so let's show that KH is actually equal to the return ratio. Okay, so why is that true? Well, let me take my system. Let me put a test generator here. And let me short the input, right? And let me observe the signal here. Well, if I go back to my equations, I have SIC is B1 SN minus H SOC. Well, SN is shorted, so SIC is minus H SOC. And then there's another generator here, which is K times SIC. So I could say that the return signal is K times H SOC, right? Well, SOC is actually my test signal that I injected. So in fact, R, which is minus SR over ST, is just KH. Okay? So that's the first piece of the puzzle. In this equation, this term here is really the loop gain. Okay. Now, it's a little bit upsetting that we don't just call this T, right? Why do we call it R? Again, I'm being a little consistent with the book. I would just call it T. It's the loop gain. The book chooses to call this the return ratio because it's slightly different than the loop gain you would get if you use the two-port analysis. And that's because the two-port analysis assumes that this term D is not here. It forces your system to look like this. So you get a slightly different answer. But really, this is what we care about, right? This is the feedback term. So KH is the return ratio, is the loop gain. Okay? Questions about that? Okay, so now let's write the gain as D plus B1 K B2 1 plus R. And let's define G as just this product. Okay? And I'm just going to manipulate this equation to get it into a form that I like. So this is the form that it's in right now. I can put this under a common denominator, so I have D plus dr plus G 1 plus R. And then I could substitute, actually factor an R term here. So I have R 1 plus R D plus G over 1 plus D over R. Let me just do this a little careful. So here I have, let me just write this as D 1 plus R plus G 1 plus R and okay, so what I do is this is here, just this term here, and then I group these two terms together. This term doesn't have an R, so I just get G over R. Okay. So you might think we're crazy to put it into this form, right? I mean, what did we accomplish? It's the same equation, right? Well, it turns out that this equation is a little bit more insightful. In particular, let's define A infinity as G over R plus D. Okay. What's the significance of A infinity? I'll give you a hint. Look at this equation here.
1 over F.
Yeah. In fact, if you look at this equation and you say let the loop gain approach infinity, this term goes to 0, this term goes to 1, and you get this term. So A infinity is the closed loop gain for, so A infinity is the closed loop gain for very large R. All right, so with that definition, now I can write that my gain is A infinity R over 1 plus R plus D over 1 plus R. Okay. And so I've reduced my system into 3 important constants, which, in fact, this is really why this formulation is really important, because these constants are actually very easy to calculate. All right. How do I calculate A infinity? It's trivial. It's just the gain of your system, your circuit, when you have infinite GM. Turns out it's very easy to do this calculation. Return ratio, we've already done a few examples. We know how to calculate it. D is also very easy to calculate. It's the gain of your system when the generator is turned off. So it's just a passive network. It's a direct feed forward. In fact, if you look at this equation, you can write it as a block diagram in the following form. you have forward gain A infinity times R. You have a feedback factor which is 1 over A infinity. This is what was just pointed out. You have a negative feedback network. And, very interesting, you have a direct feed-forward network. And you have your output. Actually, the way I've written this equation, the feedback should be taken here. So this is your ideal feedback. As loop gain becomes very large, what does the gain go to? It just goes to 1 over this feedback factor, which is A infinity. This is your forward gain, unilateral gain, A infinity R. So all the forward action is captured by this through the amplifier, and then this term captures the direct feed through that occurs even without the amplifier present. Okay? And this is actually a very, once you get familiar with this equation, it's a very nice, simple way of analyzing a feedback system. And let me emphasize that to use this technique, you don't really have to identify is it series feedback or series shunt. One shot, you get the answer. So let's do an example to illustrate that. Any questions about this? Yes?
Formal way of deriving the loop gain equals A times F. This is a formal way of deriving this return ratio. How is it possible to mathematically prove that they are the same for most systems?
Well, they're not the same. That's actually one of the keys. Is if you look at this block diagram, so with a two-port analysis, we showed that under ideal conditions, we end up with a block diagram like this, right, where the D term is not there. So they're different. And it turns out that this is actually a more realistic case, especially for circuits that we analyze. And the reason is that we like to use capacitive feedback, right? And capacitive feedback at high frequencies ends up giving us a lot of feed-forward signal. And so this formulation is definitely more correct. All right, that's a good question. It's always good to do an example, because at the end of the day, you're going to forget this derivation, but you're going to remember, hopefully, how to use this technique. So here's an amplifier that maybe you're not so fond of using a two-port analysis, because we often voltage drive it, right? But we know it's actually the input has to be a current signal for the feedback to be active. All right, so let's using this approach, what we need to do is calculate A infinity, the gain when we have infinite GM. We need to calculate D, the direct feedback factor, the direct feed forward factor, and R, the return ratio. All right, so let's start out with A infinity. So this is the gain as R approaches infinity, or K approaches infinity. In this case, there's only one controlling node. In fact, I should mention that what if you have multiple controlling terminals, right? Which one do you choose? You can choose any of them. And this one, we have just one, so we'll choose that one. So K goes to infinity is equivalent to GM going to infinity. So if GM goes infinity, what does VGS go to? 0, right? I have infinite gain, so I better have 0 VGS, otherwise I have infinite output signal. So VGS goes to 0. That means that the input current, Vs over Rs, basically it can't go into my transistor at low frequency, so all of it goes through RF. And so then the output is minus In times RF, or V out over In is minus RF.
So actually, A infinity is actually A infinity at DC, or on low frequency, right?
No. This analysis we did applies at any frequency. So for simplicity, I'm doing it at DC.
But if you apply high frequency, there's a capacitance CGS. The equation is not valid.
Yeah, this is low frequency. I'm doing the calculation at low frequency, yeah. Okay, so not surprisingly, the A infinity term just works out to be minus RF. And of course, most of you knew that already, right? Because you've analyzed the circuit. And you know, as the loop gain gets very large, the feedback factor F is 1 over RF. 1 over F, therefore, is 1 over 1 over RF, which is just RF. Okay, no surprises. But notice that I didn't have to identify the type of feedback or anything. Okay, any questions about this calculation? All right, so now let's look at D. D is the direct feed-through. For K, which is GM in this case, equal to 0. So here's IS, RS. Here's RF, and here's RL. Okay, so if K is equal to 0, the transistor is really not there at low frequencies. So all I care about is the output voltage due to this current source, right? So what I care about is V out over IS. Okay, so then I just have a current divider. I have RS over RS plus RF plus RL times RL, and that's it, right? Nothing fancy. So D is simply RS RL divided by RS plus RF plus RL. All right, so you can see the calculation of D is very simple, the calculation of A infinity is very simple, and the return ratio, which is going to come up next, is also something pretty simple to calculate. Questions about calculating D?
So if
Michael.
I have more transistors, do I basically always set K GM equals 0 or infinity for all of them? Or?
Just one. Just the one you choose to be the controlling terminal. Okay, that's a good question. All right, so now let's calculate return ratio. So what we do is we break the generator. And I set the input equal to 0, right? This is IS, this is RF, this is RL. This is the point where I'm going to inject the test signal, and I'm going to short out my generator, GM, VGS, and this is the return signal. And of course this is equal to 0, so it's an open circuit. So if I inject IT, and this is RS, again I have a current divider, and then I'm pretty much done. So VGS is equal to IT times the current divider, which is RL divided by RL plus RF plus RS, times RS, and it's negative because the polarity of that current source, and therefore the return signal, which is GM VGS, is going to just be minus GM RL RS divided by RL plus RF plus RS. And so of course then the return ratio, which is minus IR over IT, is just GM RL RS divided by RL plus RF plus RS. So there we have it. We have almost everything we need, right? So to calculate now, so this is my loop gain. To calculate my closed loop gain, it's A infinity times R over 1 plus R plus D over 1 plus R. Okay? And so let me just plug in here. So what did A infinity work out to be? A infinity was just minus RF, right? So here's A infinity. It's minus RF. What's R? Well, we just calculated R. It's GM RL RS. And let me just, instead of dividing here and here, I just multiply through by this term here. And likewise here, D I calculate it to be RS over RL plus the same denominator that I have over here. So if I multiply through by the denominator, I get RS plus RF plus RL plus GM RL RS. Okay? And so now I can actually collect these terms together, and I get 1 minus GM RF times RS RL divided by RF plus RL plus 1 plus GM RL times RS. Okay, so pretty straightforward, just a little bit of algebra. At the end of the day, since this is an amplifier that we know really well, let's make sure that it actually reduces to what we would expect. So the first thing we expect is that this expression should go to the ideal expression of minus RF as the loop gain becomes very large. Okay, so let's take, for that to occur, we take GMRF gets large, GMRL gets large, and this is a good check of our algebra, right? If I had made an algebraic mistake, it would show up here, because you could just say it's A infinity, right, and not bother with the calculation. So if that happens, on the numerator I have minus GMRF RS RL. On the denominator I'll just have this term, GMRL RS. RS cancels, RL cancels, GM cancels, and I get minus RF, which is of course just equal to A infinity. Okay, so questions or comments about this calculation? Well, one thing is certainly missing. When we did our two-port analysis, not only were we able to calculate the closed loop gain and the feedback factor and the loop gain, but also the input and output impedance, right? So we need to also figure out how to do that with this formulation. Before I do that, though, I just want to point out one more thing here, and that's that you can just directly calculate this term B without first calculating A infinity and R. And it's actually a very simple derivation. So B is A infinity times R. Now going back to the original form of A infinity, it's G over R plus D, or G plus dr, just kind of unwinding our calculation. And again, G we defined as B1 times K times B2 plus dr. And then, remember R, again, I'm just unwinding back to my original terms. R is KH. Okay? Now, if I factor KB2 out of this equation, then I get B1 plus DH over B2. And what's nice about this equation is it's actually shows B as a product of three terms. I'm going to show you guys that this term is the gain, partial gain, for the output shorted. This term we already observed by definition that it's a partial gain for the input shorted. And then this K is just our GM factor controlling gain. Okay? So you, instead of doing this calculation, you could directly just find the effective forward gain using these equations. All right, and how do you do that? Well, to show that this is true, just take S out is equal to 0 in that very defining equation, right? Our defining equation was that S out is ds in plus B2 SOC. Well, set that equal to 0. So I have B2 SOC is minus ds in. I also have that SIC by definition is B1 S in minus H SOC. So now let me substitute here. I have B1 S in minus H, and then substitute here minus D over B2 from this equation, S in, and therefore SIC over S in is simply B1 plus DH over B2. Okay, and that's what we wanted to show. Okay, so that lets us interpret this term here as this partial gain. Okay, let me now close off with something that's probably the most important. Well, not the most. Loop gain is the most important, but also equally important is closed loop impedances, because a lot of times we use feedback to build better amplifiers that are less sensitive to source and load impedance, and to do that we want to show that the impedance levels in an amplifier change as we apply feedback. Okay, so again, let me draw the model that I have for my feedback amplifier. So let me say I apply a voltage Vx here, or a current if you like, and I observe the corresponding current or voltage. If I take the ratio, of course, that will give me my port impedance. So Z port, of course, is just Vx over Ix. And what I'm going to do is, let's make this a current source. Okay, so this is Ix. And then let's observe the voltage Vx. So just like I did before, since this is a linear circuit, I can write an equation that Vx is A1Ix, that's my first independent generator, plus A2Sy, which is my second not independent generator, but I'm just going to pretend it's independent for now. And likewise, this controlling voltage, SIC, is A3Ix plus A4Sy. Okay, the first thing we do is set the generator equal to 0. That, of course, implies that Sy is equal to 0, and then you can see that the ratio of Vx over Ix is just A1. And I'm going to call that Z port. K is equal to 0. So that's the impedance looking into this port when the generator is turned off. Okay? Now that's usually a very simple calculation to do. A couple lines of algebra for most circuits. Next, what I'm going to do is I'm going to calculate the return ratio in this circuit under two conditions. Under the condition that port 1 is open circuited, and under the condition that port 1 is short circuited. Okay. So let's let port X be equal to an open, so that Ix is equal to 0. And let me just emphasize that this port X can be any port in the circuit. It's not necessarily just the input port. It could be the output port. It can be an intermediate port in the circuit. All right? Okay, so if Ix is equal to 0 and I calculate R, right, that means that I inject a test signal at the position Sy, right? So I'm going to just make this an open circuit, inject the signal here, and observe what comes back. All right? So SIC, by definition, if IX is equal to 0, SIC is just A4 times SY. And the return signal is just K times SIC, so it's basically K times A4, and so therefore the open circuit at port X return ratio is just minus K times A4. Right. And again, bear with me. I know we're doing a lot of algebra, but at the end of the day, things look pretty good when you're done. All right. So now we're going to let port X equal to a short circuit, which implies that Vx is equal to 0. So let me just redraw the circuit here. Again, port X is some arbitrary pair of terminals that I pull out of my circuit, and I'm interested in knowing what's the input impedance looking into this pair of terminals. And you can guess that this answer is going to depend on these return ratios and the input impedance when K is equal to 0. All right, so now I want to calculate, again, the return signal. So I inject a signal, a test signal at port Y, and by definition, if Vx is equal to 0, I can write a relationship between Ix and Iy from this equation. Minus A2 over A1 times St. And then I have another equation. I should put these equations up here. So now I'm going to substitute in this equation. I have A3 times Ix, which is minus A2 over A1 St, plus A4 times Sy, which is also just St. And so therefore, the return signal, which is K times SIC, let me just do it a step at a time. So this gives me SIC over ST is A4 minus A3 A2 over A1, and the return signal is just K times SIC, which is K times A4 minus A3 A2 over A1. And then finally, R short is equal to the negative of this. So it's minus K times this term. I'll just write it out here. So R short is minus K A4 minus A3 A2 A1. Okay, so what does this all mean, right? Well, hopefully now that I write the general impedance at port X, which in general is equal to just Vx over Ix, it's going to be related to these terms that I've calculated, right? Hopefully. Otherwise, I've wasted my time. So let's go back to these fundamental equations here. Zx is just over Ix is just equal to A1 plus A2 Sy over Ix. And Sy is just equal to K times SIC over Ix. And SIC over Ix, if I look at the second equation here, is A3 plus A4. So let me write that as A3 plus A4 times K SIC over Ix. Let me group these terms. I have SIC over Ix, 1 minus KA4 is equal to A3. And so now I can substitute here into here, so I have Zx is equal to A1 plus A2 times K times A3 divided by 1 minus K A4. That look right? A1, A2, K, A3, yeah. And so now you just do a little bit of manipulation, and I guess I don't want to bore you guys, but yeah, just put it under a common denominator. And then factor out an A1. And I have 1 minus K A4 minus A2 A3 over A1 factored out 1 minus K A4. Okay? And so now it's finally in the form that I can use, because you'll notice that it's getting messy. First of all, A1 is just the port impedance when K is equal to 0. Minus K times A4, well, that's the return ratio for open circuit at port X. So here I have 1 plus R open. And here, if you remember, K times A4 minus A2 A3 over A1 is R short. Again, this big mess here. So this term is R short. And so the impedance looking into any port of the circuit is equal to the impedance looking in with the generator off times two factors, times 1 plus R short, which is the return ratio for that port shorted, divided by 1 plus R open, the return ratio when that port is open circuited. Okay. This equation is known as Blackmun's impedance formula. And again, it has this nice property that it lets you be stupid, right? When I use this equation, I don't have to know what kind of feedback there is. If this term tends to dominate and the impedance goes up, I know there's more series feedback at that port. If this term dominates and the impedance goes down, I know there's more shunt feedback at that port. But automatically in the calculation, one of these terms is usually 0. And that tells you what kind of feedback is actually happening at that port. Okay. Questions or comments? Should have numbered these pages. Okay, so let's do a quick example, just a follow-up. So let's say I'm interested in calculating the input impedance of this amplifier at this port. And I want to use this Blackmun's equation. Okay, so first thing I do is calculate the input impedance with K is equal to 0. What is that? K is equal to 0, transistor's not there, it's just these two resistors in series. All right. What about the return ratio for open circuit at port 1? Well, let me just quickly draw an equivalent circuit. So what I want to calculate is VGS when I inject a test signal. Well, because this circuit is open circuited, all the current has to flow into the output. And VGS is just equal to the output, right? So VGS is equal to Vout is minus IT times RL, and the return signal is GM VGS, so it's minus GM RL times IT, and so therefore the R open is just plus GM-RL. Okay. Simple calculation. Okay. Let's just go through that real quick. So to calculate the return ratio under open condition, I leave the input terminal open, right? So this port is open. I inject the test signal. I didn't draw this shorted generator. And here's the return signal. Right, so I inject this signal. Since this port's open, all the current flows through RL. That produces V out, which is equal to VGS. And then GM times VGS is my return signal. All right. How about R short? Okay, so R short means I take my transistor, short the input, and calculate the return signal. Well, if VGS is equal to 0, the return signal is identically equal to 0, so R short is equal to 0. So now I use my equation that Z is equal to Z K is equal to 0 times 1 plus R open divided by 1 plus R short. Get that backwards? Yeah. You do have to remember something. All right. So in this case, R short is equal to 0, so it's just ZK is equal to 0, which is RF plus RL, divided by 1 plus R open, which is just GM-RL. Okay? And if GM-RL is very large, this is roughly 1 over GM RF plus RL divided by RL, which is exactly what you should hopefully expect, because this is shunt feedback, and it should lower the input impedance. And you can see now the input impedance looks like a diode-connected transistor times the feedback factor. And that makes sense, right? Because only a fraction of the output signal excites the GM generator. Questions or comments? Yes?
If we would use the two-port analysis, would we get the RL in the numerator? Would we get that RL?
If we did the two-port analysis, we would get Z in divided by 1 plus T. And I don't... Check it. Yeah, I'm not sure. If the answers are actually different, this is more accurate, because we didn't make any approximations when doing these calculations, right? Okay, so again, I apologize for going through this in detail if it was boring, but I think most people haven't done the return ratio analysis before, so it's worthwhile to do it. It's actually a very powerful technique. Let's switch to next topic, which is a little bit lighter. It's basically just how do we do this in SPICE, right? Now we know how to do it by hand. So the next question is how do we do it in SPICE? So let's switch to the laptop. Okay, so here's a circuit that we talked about earlier. And so what I did is I went in SPICE and calculated the loop gain just to confirm my hand calculations. And finally I got it to work. But one thing you'll notice is that I'm using Spectre here, and so all I did was I put in this probe, this current probe, somewhere in my feedback loop, and then asked SPICE to do stability analysis. It's great, right? I'm done. SPICE, new versions of SPICE have stability analysis built in, so you don't have to do any extra work. For those of you who don't appreciate that, let's look how this was done in the old days. Okay. So in the old days, this might be one technique for calculating the loop gain, right? So somebody would say, first of all, in SPICE, I don't have access to controlling nodes, right? Those are internal to the model. So I can't break the loop at some controlled source where the loading effects would be negligible. So what I have to do is I somehow have to break the loop, make sure that the circuit still biases up correctly. Oftentimes the feedback also biases my circuit. And then I have to somehow take into account the loading when I've broken the loop. So for instance here, in this simple feedback amplifier, let's say I break the loop at the gate. Well then the gate needs to be biased, right? So I'd have to now bring in a separate signal to bias the gate. Or one nice technique is, in this example there's capacitive feedback anyway, so the feedback's not helping. But imagine if this were shunt feedback with resistors, and actually the actual DC voltage at here were equal to the drain voltage, which were set up by some other feedback loop. So a lot of people don't quite, one trick you can use is you don't quite break the loop. You put, basically, in this case, since there's no current flowing, I can put a huge resistor. And that resistor means that the DC voltage here and here is equal, which in some circuits can be helpful. In this case, it's not a good example. What could I use in other circuits where there is current flowing? Let's say I wanted to break the loop, but I still want DC current to flow. What's a convenient element to do that? You could use a controlled voltage source. That's one way to do it. An inductor, yeah, actually, you could use a huge inductor. So instead of this resistor, I could put an inductor with, let's say, 10 to the 15 henries. SPICE doesn't care, right? SPICE has no idea. As long as it converges, it's happy. So you just put a huge inductor so that at low frequency you still have essentially an open circuit. But then that helps your DC conditions, right? But then you have this problem with the loading. This node here sees the CGS of this capacitor. So you could put a mock load. You can say, well, I can put a test signal in here, find out what CGS is, and then put it over here. Well, what's the problem with doing that, besides being kind of not very elegant? Well, it's complicated, right? Because there's actual Miller effect here, so this capacitance gets Miller multiplied, and that Miller effect has feedback in it itself. How do you take that into account? Right? It gets pretty messy. So this is the old-fashioned way of doing it, and trust me, I've done it like this, and many people still do it like this. If you're careful about what you're doing, you pretty much get the right answer. But there are better ways of doing it. And one better way of doing it is actually a technique developed by Middlebrook. And I won't go through all the detailed derivations, but I'll just point out how you do it. So the idea here is that you're representing your circuit as an equivalent circuit that looks something like this. Of course, this is not, you have to simplify your circuit a great deal to put it into this form, but essentially, at the end of the day, you could put it into this form. And if you do that, then the loop gain is very easy to calculate. It's just given by this simple expression. So the whole idea of this Middlebrook technique is to understand what the equivalent Z1 and Z2 are in your circuit. So let me show you how that's done. So what you do is you inject two kinds of signals. You inject a voltage signal in series and a current source in shunt. What's nice about this is that since the voltage source is in series, it has zero DC voltage, so it does not upset the DC conditions in your circuit. The circuit still biases up correctly. And when you do this calculation here, you calculate Vy over Vx, which is called TV. Okay? And you do the same thing with a current. Inject a current in shunt. Again, the DC current is zero, so it doesn't disturb your circuit. And you end up calculating Ti. And if you solve these two equations, the loop gain and these two equations, you come up with this nice formula, which tells you that the loop gain is some combination of TV and Ti. Kind of almost looks like a parallel combination, right? And so you can guess that in a lot of circuits, one of these T's is going to dominate the calculation. All right. There's some numerical issues with this calculation. You can get, basically for certain conditions, you can get really bad overall numerical stability in this equation. But trust me, you don't care. The conditions under which it happens are cases where you don't really care about, where the loop gain is very small, for instance. Okay, there's a variation on this approach that doesn't have the numerical stability issues. Again, I won't go over it. There's an example at the end here which uses this technique to calculate stability. So it's a simple amplifier, and what you do is you build yourself a block called the loop gain block, which automatically does all these calculations for you. And the SPICE netlist is here. It's in Spectre format. And again, I encourage you guys to look through this. The way it does the calculation is it kind of does dot alter analysis. So it calculates the loop gain with a current injection, calculates it with a voltage injection, then takes the sort of like the parallel combination, and you get the overall T. And so here is actually the result. It's a little bit hard to read. Let me just point out that this curve here, which is the blue curve, which is kind of the low-pass transfer function, is the total loop gain. And then the intermediate, these are the intermediate TVs and TI. So this is kind of like, I'll loosely call the voltage loop gain and the current loop gain. And what's interesting is that you can see here that the smaller one always dominates. So at low frequencies, it's the TV that dominates, but at high frequencies, it's actually the TI that dominates. This is also the loop gain, the total phase, basically the phase of the loop gain. And you can see the simple circuit is very stable. It has 90-degree phase margin because it just has one pole. The circuit is so simple you can analyze it by hand. This is the circuit. Basically, you just, even though it has capacitive feedback, there's nothing different about this circuit than the example that we did. Inject a test signal here, calculate the return signal. It's a trivial calculation. This is what you get for the loop gain. It's a single pole system. And you can calculate the unity gain frequency from this. And you can check the phase margin. Of course, it's 9 degrees. It's very simple. Let's see. Probably we go back and talk more about stability. All right, so there is one issue. There's actually usually more than one loop in our circuit, right? A good example of that is the Miller feedback. Right? Every transistor has its internal feedback, and every transistor has source degeneration, right? So it has its own local feedback, if you like. So how do we deal with all these multiple feedback loops, and how come everything kind of works out? Well, it turns out that if each loop on its own is stable, and you put them all together, everything kind of works out. You don't have to worry about it. And in fact, the way we design our circuits is we intentionally put in our compensation capacitors in such a way that the poles for these various loops don't interact, right? Otherwise, our phase margin is going to suffer. So in essence, by design, we're going to make sure that these loops don't interact. There is one loop that we have to be worried about, and that's in a fully differential amplifier. So in a fully differential amplifier, by definition, there's actually two feedback loops, right? There's the differential feedback loop, right? And then there's a common mode feedback loop. So the common mode feedback loop, just pictorially, is going to take the average voltage here, gain it up, and then do something to the amplifier to stabilize the average voltage. Well, with a fully differential amplifier, we actually are in luck because by definition, this amplifier doesn't respond to common mode signals. So this differential feedback loop is pretty much immune to any kind of common mode signal. So already the differential loop and the common mode loop are decoupled. So we don't have to worry about these two different feedback loops interacting. Okay. What else is important here? All right, so at the end of the day, you've done your, let's say, your return ratio analysis or your two-port analysis. You've run SPICE. Everything looks good. You have enough. Again, remember, let's get back to the goal. The goal is to design a stable amplifier. So you did all this work. At the end of the day, what do you check? You check your phase margin, right? You have enough phase margin. It looks good. Are you done? What else could go wrong? Noise? Yeah. But we're talking about stability. Is the amplifier stable? Yes. Michael?
Yeah, we need to check the large signal behavior and settling and startup and all this stuff.
Yeah. Remember, what we've done is we've done a small signal analysis, right? And these are very nonlinear circuits, right? Remember last lecture we looked at the GM of a transconductor, and it has that characteristic S shape. So that means that the GM is varying as a function. So this is GM versus V in. As the input signal varies, the GM varies, which means the loop gain varies, which means really, you know, there could be points where the loop becomes unstable, right? So really, we have a nonlinear system, and we've linearized it, and we've checked that the linear model is stable. You know, that gives us good confidence that it's probably going to be stable, but we definitely still have to run transient analysis. Okay? And transient analysis is a good way of checking stability, especially if you look at step response. So some of the things you might want to do in transient analysis is do a step at the input, observe a step at the output. The good thing about a step function is that it's kind of like a hammer hitting a table, right? It excites all the resonant modes in the table. It has very good frequency response. You can do a ramp response, so you slowly vary the input. And in effect, you're checking the stability for each input voltage as you vary the input. You can charge up some capacitors with some charge. In other words, use some initial conditions and make sure that initial charge is dissipated in the circuit. If you guys took 142, you know that a lot of circuits you put them into SPICE and they're supposed to oscillate and they don't oscillate. And you can say, what's going on? Well, you need an initial condition. So you either step the power supply or you put some initial condition on a charge, on a capacitor in your circuit. Okay? And you know, here's a quote from Nyquist, which basically you all know what the Nyquist criterion is if you've taken a control class. But at the end of the day, you know, you really do have to run this transient analysis to get the large signal behavior. Okay, lots of good references for you guys if you're more interested in this feedback material. I'll take any questions on feedback. So in some ways we did things a little bit backwards. We started out looking at noise and feedback systems, and a lot of you were still a little bit shaky with feedback based on kind of what you guys came and told me in office hours. And so now I think you have a good, nice background in feedback. You can go back and look at the noise and feel much more confident about that material. Yes?
With a nice formulation for Y in, Y out, and gain for Y parameters. Right, what if we brought in the H parameters? How does it look like? Is the form pretty much the same? Like,
Yeah, that's a good question. So it turns out that if you can derive the voltage gain using y parameters and actually just change all the y's to z's, and you get almost the same answer. Actually, you get exactly the same answer. It turns out that in that two-port analysis that we did, you can very clearly show that the input impedance, like if you go from y to z, instead of instead of admittance, it goes to impedance. But otherwise, the equations are exactly the same. With hybrid parameters, it's almost the same. There's a little bit of small difference, but I encourage you, go calculate the voltage gain with, let's say, h parameters, and then compare it to the equation with y parameters. Exactly the same. So all the conclusions that we had about y parameters apply to all the two-port parameters. Okay, that's a good question. Okay. Any other? Yes, Shiji.
So in the two-port analysis, we cannot model the direct path, but in the return ratio, we can model everything.
Yeah, you can't model it in the same way. So you can still model. So here's the problem with the two-port analysis. With the two-port analysis, if you look at the expression for voltage gain, it has basically, well, let's just look at an example. So one of the things that we were able to do, so let's say this is our transistor, and let's say with two-port parameters, I want to calculate basically this forward path without this transistor, right? If you write your two-port equations, you'll find out that there is no natural way for doing that. You know, in our two-port parameter analysis, by setting y12 equal to 0, we got rid of feedback. And that's how we derived our loop gain equations. Well, you might think, well, what if I set y21 equal to 0? Does that give me the feed forward through this network? Actually, no. If you set y21 equal to 0, you decouple the system completely. And so the problem with our two-port analysis is that it's not easy to split y21 into a y21 passive plus y21 active. You can do it. It's messy. It's not as clean as the approach that we just showed.
Model the direct path, but just in different ways.
Yeah, the two-port analysis, again, if you go back and look at it, it's pretty general. That two-port can be anything. It can have feed-forward path. But when we put the equations into a form of a over 1 plus t, we forced it so that you couldn't have a direct feedback path occurring outside of that loop. Okay? Kind of subtle point, but it's interesting. All right. Any other questions? All right, so I think it makes sense to start the settling time discussion next lecture.